In continuation with our discussion on nitrogen containing organic compounds, I stopped at the stage of aromatic nitro compounds. Aromatic nitro compounds means the benzene ring or a higher homologues of benzene like naphthalene, anthracene, phenanthrene etc., will be there in one part, and nitrogen should be attached either inside the ring or as a substitution. So, I started with a substituted benzene derivative or nitrobenzene, and I said that our main aim in the first part was the preparation and use of aromatic amines. So, how from aromatic nitro compound we can prepare the aromatic amines? That is by simple reduction, and that could be used by simple reagents like zinc, commercial zinc and dilute hydrochloric acid to prepare nascent hydrogen, which in situ can convert the nitrobenzene to the aniline. So, aromatic amine preparation will not be difficult if I take two steps, that is electrophilic substitution reaction to make the carbon nitrogen bond and then reduction. Now, electrophilic substitution reaction is very interesting phenomena in aromatic chemistry. The reason I said that benzene ring is electron cloud or electron dense thing, it will form pi complex very easily with electrophile, then it will form the sigma complex and then give the product or re-aromatize to get the product. That product is nitrobenzene. Now, if I write the structure of nitrobenzene, N double bond O and O. So, what I see that NO2 group, a coordinate bond and a double bond being shown. This NO2 group will pull electrons from the benzene ring, not push. So, because of this pulling electron from the benzene ring, what will happen to the benzene ring? Benzene ring will lose the electron density, and if it loses the electron density, then its carbocation character will be developed in the benzene ring, and you know, if there be more nitro group in the benzene ring. One simple example I am writing here, a known compound is 2,4,6 trinitrotoluene. This is toluene, 2 position there is a nitro group, 4 position there is a nitro group and 6 position there is a nitro group. So, 2,4,6 trinitrotoluene is a very important compound. You know, this is for other purpose being used. This is called TNT for dynamite in dynamite or other compound. These are the compounds being used, and these nitro highly substituted nitro aromatics are explosive in nature. So, this is another interesting features of carbon containing nitrogen compounds or nitrogen containing organic compounds, where the nitro substituted aromatic ring, the electron density of benzene ring gets reduced. As a result, it becomes the carbocation in character, and you can see one very interesting features. If there be more nitro substitution, as the electron density is decreasing, the explosive nature is also growing. One such example is TNT, many other derivatives are there, and you know another compound that is also very interesting in the nitro substituted thing, that is phenol. When being nitrated with sufficient amount of nitro group, that ends up with 2,4,6 trinitrophenol. Similar to TNT, this is called picric acid. Picric acid is also a very interesting compound, which is present which when reacted with an aromatic compound form a charge transfer complex, and this charge transfer complex where say phenanthrene or naphthalene is the donor because it does not have any substitution, and picric acid is the acceptor to form a very nice colored charge transfer complex. So, those things are also used for the detection of polyaromatic hydrocarbon, PAH, polyaromatic hydrocarbon. So, what it does, more electron rich benzene ring, I have taken some other derivative, some unusual type structure, pyrene etc. So, that donates the electron and nitro group containing benzene ring accepts the electron. That means, we are able to make a benzene ring electron deficient by putting the electron withdrawing group on the benzene ring. One such example is nitro, other may be fluoro or trifluoromethyl. Those groups are electron withdrawing. As a result, what happens? The benzene ring gets carbocation character, and then it could be reacted with a nucleophile to make directly the nucleophile attacks the benzene ring, and direct carbon nitrogen bond formation will be possible. So, that is a way out. Question comes, how you can make the benzene ring electropositive? Answer is taking up electron with the help of electron withdrawing group like nitro, fluoro, trifluoro, and that will help, and more number of electron withdrawing group, more the carbocation character will be there on the benzene ring, and then the nucleophile should attack the way it was attacking with the aliphatic system. And so, in that way the nucleophilic substitution in the benzene ring is also possible. That is another way to make carbon nitrogen bond in the organic chemistry. Okay. Now, as I want to tell you, when in benzene ring there is a group being present, I have taken an example of methyl group, and I want to do or I want to introduce a nitro group, because we are talking about the nitro group NO2 plus introduction to the benzene ring. How we did in the previous case? We started with benzene treated with NO2 plus. Question comes, where is the source of NO2 plus? You know one very interesting reaction to get the NO2 plus. In the textbook it is written as MA. MA is the abbreviation of mixed acid, mostly nitric acid and sulfuric acid. What concentrated nitric acid and sulfuric acid is doing? It is generating NO2 plus, because sulfuric acid is also a good dehydrating agent. From nitric acid it takes off the water and generating a NO2 plus or the electrophile. So, electrophile is ready as the NO2 plus, and the benzene ring is ready, and they can form pi complex, sigma complex, and then the substrate. So, in that way benzene getting converted to nitrobenzene very easily by a electrophilic substitution reaction. What is being substituted? The hydrogen atom of the benzene ring, one of the hydrogen atom of the benzene ring, who is entering NO2 plus, and by that way we are able to make a nitrobenzene. My question is, if a methyl group is present there and now you are doing a MA or mixed acid treatment, that is NO2 plus being generated and being introduced, where it will go? That terminology to know where the second group will go when there is a monosubstituted benzene ring, the terminology is called orientation. So, what is the orientation of the group and how we can determine the orientation? That depends on several factors. One of the factor is, of course, electrophile is a must. Second factor is, you are treating the benzene ring with a substitution. What sort of substitution is that? Is it an electron donating group or it is an electron withdrawing group? Say in this case methyl, how should I know it is electron donating or electron withdrawing? Because the carbon hydrogen bond each, if I take elaborately, the electronegativity difference of hydrogen and carbon is there. So, electron pair forming the bond between hydrogen and carbon will be pushed towards the carbon atom. So, 3 such push will be there from 3 sides. So, what will happen to the carbon? The electron density will increase, and that electron density it will again relay to the benzene ring. So, what will happen to the benzene ring? So, electron density gets increased. So, compared to benzene, the toluene, methyl substituted benzene toluene, the electron density of the benzene ring is getting increased by the inductive effect. Now, if I bring the nitro group that is coming from mixed acid, so what it will do, in which position this NO2 group will enter, that we can write by some structure, like because of this push the carbon, this carbon's electron density is increasing. So, this may be polarized in this side. So, I said write a structure clearly that this double bond is now being localized, and you are ending up with the methyl group, and this double bond is now polarized over here, and this can delocalized on 3 sides, and those delocalized structures are the resonating structure. What is that? This type of delocalization. We can again delocalize this negative charge on this side also, and by this way we are able to make CH3, 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 and the negative charge is getting delocalized in this side. So, where we are able to put the negative charge? If I put the substituted benzene rings, that is methyl group as the carbon number 1, this is carbon number 2, this is 3, this is 4, this is 5, this is 6. So, we are able to make negative charge or localize negative charge at 2 position, 4 position or 6 position and no other position. So, what does it mean? The electrophile should enter either in 2 position or 6 position, they are equivalent, or in 4 position, and these positions are called ortho, meta and para. So, in this way ortho, meta and para. So, in one way we are able to see that electron donating groups are ortho para orienting. What does it mean? That if in benzene ring some group is there, I have taken one example, that is methyl. It is not restricted to methyl, any other chloro or any electron pushing group or tertiary butyl, whatever, which can increase the electron density of the direct benzene rings carbon atom where the attachment is there, then it can relay the electron pair either in 2 position or 4 position or 6 position. 2 and para orienting. That means, now it is very simple. If I start with toluene, make one equivalent of the nitro group, then it will end up with ortho or para substituted benzene ring. So, this is para, this is ortho, mixture of ortho and para substituted, and amount of ortho and para depends on several factors. One of the interesting feature is the steric factor and the reaction condition. But if we do further nitration, then what will happen? That means, to this if I put one more nitro group NO2 plus, that means sufficient amount of mixed acid. Now, there are 2 functional group already present in the benzene ring, where the third electrophile will enter, though the electrophile is similar in nature, that is NO2 plus. So, that NO2 plus will not dictate, but the groups being present in the benzene ring, that is methyl and NO2 plus, they will say that which position will be suitable for that. That means, electrophile should enter in 2 substituted or 2 nitrotoluene or 4 nitrotoluene in some positions. Let me show that. What is that? CH3 group is electron donating, nitro group is electron withdrawing. Very interesting phenomena. One is electron donating, another is electron withdrawing. I have written that electron donating groups are orthopara orienting. I can also write electron withdrawing groups are meta orienting. Electron donating groups are orthopara orienting, electron withdrawing groups are meta orienting. So, because of this methyl group, this position will be activated, this is the ortho, this position is also activated, that is also ortho, and with respect to the nitro group, the same position getting activated, because nitro group is meta orienting, not orthopara. Similar fashion, this nitro group is also activated because of the presence of this position by the nitro group. So, both will help if I have sufficient amount of NO2 plus to activate these two positions. Now, if I take this structure, that is orthonitro-toluene, what will happen? Methyl group is electron donating. So, this will help to introduce in ortho and para position. This is the ortho position, this is the para position. Nitro group is meta orienting, this also helping to activate the same position, that is meta. With respect to this, this is the 3 position 1 3. So, that is meta. So, both the groups are helping to get the new electrophile or the same electrophile to come in the position marked as cross or right. So, what will be the end? End will be you end up with CH3, NO2, 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 both the cases. So, you get a single product. That means, nitration of toluene with sufficient amount of mixed acid should produce 2,4,6 trinitrotoluene, or what I have written here as TNT. So, in this case, two things we have discussed. One is electron donating group helping to come to enter for the entry of the electrophile in ortho and para position, and electron withdrawing group is helping to enter in the meta position. If they contradict, then it is very difficult. If they help each other, means one is the complement of other, then we get sufficient amount of one type of product. And when a competition takes place between the electron donating and the electron withdrawing, normally electron donating groups getting little bit preference, but that is not the case in this case. So, this is the way the nitro substituted benzene ring could be produced, and as I said, then by reduction the nitro group could be converted to the amino group. So, if I start with a nitro substituted benzene ring, that I stopped, what will happen? Why this nitrobenzene will help the new electrophile to enter only in the meta position, that we can show with the help of a resonating structure, because the nitro group is electron withdrawing group, it is pulling electron from the benzene ring. So, what will happen? We get some sort of structure where we get the negative charge where you get the negative charge getting delocalized on the nitro side, and a positive charge is getting localized on the ortho position. And this can have in a similar way the same sort of resonating structure. If I keep the nitro group intact like this and play with the delocalized thing, what I see, the positive charge getting delocalized from 2 to 4 position, and by another way this positive charge again could be delocalized in the 6th position also. So, what is happening here? this is the ortho position, 2 position, this is the 6 position, also ortho position, this is the para position. So, these 3 position, that is ortho and para, is positively charged. So, if you bring an electrophile which is positively charged, will not enter there. What is the second possibility? That will enter exclusively to the meta position. So, that is the reason if I start with nitrobenzene, I will end up with 2,4,6 trinitrobenzene. What is that? Nitro group will deactivate the benzene ring, will pull electron, help the second nitro group to come in the meta position. So, I am writing another NO2, and that nitro group will be entered by this pi complex, sigma complex, that same methodology, the 3 position. And now, very interesting thing has happened, because this nitro group will activate this meta position, and the other nitro group also will activate the same meta position. So, if I do a further nitration with NO2 plus, I will end up with NO2, NO2, NO2. That means, starting from this, we are able to make 1,3,5 trinitrobenzene. So, benzene on nitration gives nitrobenzene, nitrobenzene on further nitration can give 1,3-dinitrobenzene, 1,3-dinitrobenzene on further nitration should give 1,3,5-trinitrobenzene. So, this is one way out to make carbon nitrogen bonds by the help of electrophile obtained from simple mixed acids like NO2 plus. That electrophile now should enter the benzene ring in 3 positions, and when all this thing is done, if I do further nitration, then question comes where it will go. Actually, now there is no vacant position available over there, and this will not be a good way to proceed further, because this will be an awkward mixture of several things will take place. So, there is no activation or help by the group already present in the benzene ring. So, this is the general rule for orientation. When one group is there, how the second group is coming. If the second group is there, if they are complementary to each other, that helps. If not, then of course, the electron donating groups gets little bit preference. If they complement, then it is a very nice way to make the substituted compound or the products. So, this is one way to make the nitrobenzene very easily. Another thing I should say, that nitrobenzene to substituted nitrobenzene or more positions in the benzene ring, more nitro groups could be attached, and as I told you that oxidation reduction steps are very simple. You can convert nitro to the amine very easily, and this amine, that is this aniline, like the methylamine I started with, is a very important starting material, because from here you can make many interesting carbon nitrogen compound. You know, one of the reaction is treatment of aniline with nitrous acid at lower temperature, say 0 degree centigrade. What will happen? If I treat aniline with nitrous acid, what is the source of nitrous acid? Sodium nitrite and hydrochloric acid. If I mix them together, it will form nitrous acid HNO2 and NaCl, sodium chloride. And at lower temperature, this amine, when treated with nitrous acid at ice cold temperature, then we see a very interesting thing, that is, I should say, a species like this, N2 plus Cl minus. What you call this type of compound? Because in this case I can see that 2 nitrogen being attached and the counter ion is the chloride, as hydrochloric acid being used. So, this type of compound will be called di means 2, aza means nitrogen. So, diaza compound or diazonium salt, better, diazonium salt. And this diazonium salt is very interesting if 2 alkaline beta naphthol I am writing, this is the benzene ring, this is the naphthalene, this is the 1 position, this is the 2 position. In 2 position, if there be an OH group, this compound is called beta naphthol or 2 naphthol, and this beta naphthol in sodium hydroxide or potassium hydroxide solution, very interesting feature. 2 alkaline beta naphthol either in sodium hydroxide or potassium hydroxide, if we add this diazotized or diaza compound, diazotized aromatic compounds, very simple case is diazonium salt like this, we will get a very nice beautiful red color dye. What is that? A long delocalized, a naphthalene ring getting delocalized to the other benzene ring through the nitrogen double bond. So, long delocalized electron cloud is being formed, and because of that the compound is found to be deep red in color. So, a red dye is being formed by this way. So, what I should say that aromatic amine could be detected through the formation of a red dye, and this is a very good confirmative test for aryl amine, especially aniline when being diazotized. And remember, 2 alkaline beta naphthol, you are adding the diazotized compound, not the other way around under cold condition, then it forms a red dye, and that red dye is very characteristic. Why this is more colored or deep in color, why it is this? That could be explained by a very simple phenomena. There is a very general rule, if there be a long conjugated polyene system, as in this case, one benzene ring, second benzene ring, that is naphthalene, third one is also connected through the nitrogen double bond. So, it is a long delocalized system. So, when the electron cloud is getting spread over long or many atoms, then what will happen? If you think in this way, E is equal to h nu, and when a more conjugated polyene being taken, that energy to take it from the ground to the excited state will be much less if there be more conjugation than when it is an isolated double bond or simple benzene ring like this. What does it mean? If the energy needed is less, h is Planck's constant, nu 1 also will be less. If nu 1 is less, what is the lambda? Reverse of frequency, that is nu. So, lambda will be more. So, what is happening? In other way, a simple butadiene and you take a carotene, tetrasubstituted butadiene or long polyene. The long polyene or carotene, that is C40, is colored, red colored, that is being present in tomato and carrots. Why those are red or orange in color, but butadiene is colorless? Answer is because it is more conjugated. More conjugated means the more delocalized of the electron is taking place, and in that case the energy necessary to take, needed to take from the ground to the excited state, which is very important phenomena for the colored thing, is less. So, as energy is less, frequency is less, frequency is less means wavelength more. We can see 400 to 800 nanometer, 200 to 400 is the ultraviolet region. So, the compounds getting colored. So, this is another general technique. By the help of carbon nitrogen chemistry, one can make a colorless to colored by putting more conjugation, especially with some chromophoric group or oxochromic group, that also help. So, this is a offshoot or the bonus of carbon nitrogen chemistry. So, what is the advantage of that? Advantage is tremendous. Suppose you have converted a diazo compound. The way I said, take the aniline, very simple case, diazotize it with nitrous acid and get the diazo compound, and now you want to remove the diazo compound and put some substitution, because now the N2 plus is directly attached over there. You can do it in very nice way. There is a term I have written here as CuX and HX, cuprous halide, or X may be many things, cyanide, chloride, etc. So, what will happen? The whole thing, this N2 plus Cl minus will go and the X will be inserted straight over there. That means, from this diazo compound you can get the cyano compound, and in that way you can make many interesting aromatic compound, and we will take some more example little later, but this type of reaction was first studied by Sandmeyer. So, this is known as Sandmeyer's reaction. So, one of the way to make the several substituted aromatic compounds is by the help of carbon nitrogen compound through this diazonium salt, and then with the Sandmeyer reaction, where CuX and HX be the reagent, X is chloride, bromide, cyanide, etc. Okay. So, I started with amine, first aliphatic, then aromatic. Question comes, not only aliphatic and aromatic where the direct carbon nitrogen bonds is a single bond, there may be a carbon nitrogen bond as a triple bond or a double bond. Let me write down a very simple case. If I write this type of structure where I am putting the substituent as CH3 CH3 double bond, of course, I have to satisfy the valency as NH. Here the case is different, that is not a single bond, but there is a carbon nitrogen double bond is there. And this type of compounds are also very interesting. These are called not amine, but imine, and they could be prepared the way I started, that you can break this molecule and get some clue as synthone or synthetic equivalent, and then ending up with the starting material as simple as acetone and say ammonia or derivative of that. So, if we treat acetone, now the starting materials are amine and acetone together, what will happen? This is the electron rich, this is the electron deficient. How did I know? Because carbonyl group's carbon is positively charged, oxygen is negatively charged, there will be a polarization possible, because oxygen is more electronegative compared to carbon. So, electron pair forming the bond will be shifted more towards oxygen. So, making the carbon as electropositive. So, the amine will go over there very easily, and in that process you get CH3 C CH3 O minus, and this side is NH H2, and one of the hydrogen, if I put it in this way, will be picked up by the O minus. So, you end up with CH3 C CH3, and this is now OH NH H. So, this is the way the amine group and the OH group has been introduced to the acetone moiety. OH is coming from the carbonyl and NH2 is coming from the ammonia. Then what happens? This type of compounds is very interesting, because simply by heating it loses water. It loses water means how? The one of this nitrogen hydrogen bond leaves, at the same time the OH also leaving the system. So, H and OH leaving the system at the same time. What type of reaction is this one? This is called an elimination reaction. Elimination reaction. So, in elimination reaction what is happening? You get CH3 CH3 double bond NH. So, one simple way to make the imine from amine, ammonia in this case, or substituted ammonia also you can take, is very simple reactions where a nucleophile is attacking a carbonyl carbon, the nucleophile is the ammonia or substituted ammonia, and then an elimination reaction is taking place where the hydrogen and hydroxy group is leaving at the same time. This type of elimination is called beta elimination, and one of the interesting features is anti group, means hydrogen and OH. This is not a very simple complicated one, this is a very simple case, hydrogen and OH leaving the system at the same time. So, this is a beta elimination reaction by which we are able to make the imine. So, carbon nitrogen single bond we have discussed in details, carbon nitrogen double bonds also are very important, and from there many interesting compound could be prepared. One interesting compound I can say that one very reactive compound could be prepared by this way is carbon double bond N, and if we put some substituents over there could be oxidized, and this oxidation is very interesting to make a oxidine nitrogen oxygen carbon containing compound. These are also very important and very explosive nature compound. So, this is another field which is coming originally from nitrogen containing organic compounds. Okay. Third thing what I left is a carbon nitrogen triple bonded compound. That means, how to make carbon nitrogen triple bonded compound and what is the use of that. I can take a very simple example. Let us satisfy the valency of carbon RC triple bond N. Usually in organic chemistry these are not called cyanide, these are the nitrile. So, this nitrile when gets hydrolyzed, means treated with water in presence of little bit acid or alkali, what will happen? That means, RCN treated with H2O in presence of H plus or OH minus. What will be the product? Nucleophile definitely will attack this carbon, and this carbon nitrogen bond out of the triple bond one will be polarized towards the nitrogen atom. So, what I see RCOH H, this will be the positively charged, and then one of this bond has shifted. So, this will be the minus over here, that is the negatively charged, this sort of things will take place. So, obviously, this is not a very stable species. So, what will happen? The hydrogen could be picked up by this N minus. So, it ends up with RCOH, and this side will be double bond NH. RC double bond NH and OH. This type of feature again we have ended up with a triple bonded to a double bonded thing. But if I write that this can be stabilized in a way like this, the electron cloud is shifting in from one to the other, and a very interesting phenomena, and here I have written the reversible sign, not a electron delocalization. This is a phenomena where the proton is shifting from this position to that position. Proton delocalization is another way to call it is tautomerism. So, tautomerism is taking place, and we have ended up with a compound is RCONH2. What is that compound? This is the amide. So, from nitrile we have ended up with an amide. How? By hydrolysis. What sort of hydrolysis? Either acid catalyzed or base catalyzed. What is happening to RC triple bond N? It has been converted to RCONH2. So, amide being formed from the nitrile, and amide is a very important structural features. From here we can make polyamide, then many other polymeric materials which are used in everyday life. So, polyamide is a very important feature where the starting material is coming from the nitrile. So, carbon nitrogen triple bond is also being mentioned over here, carbon nitrogen single bond, carbon nitrogen double bond and carbon nitrogen triple bond, and that could be converted to RCONH2. Sometimes I ask my students that I have done this reaction from alkyl cyanide to the amide by hydrolysis in this way. And let us take an example. Suppose I have given you acetamide CH3CO NH2 and I want to get acetonitrile, that is CH3CN. How to do that? People get confused, but a very general rule is, if from nitrile to amide you do the hydrolysis, means breaking with water. So, obviously, from amide to nitrile, what will you do? A dehydration. And what are the dehydrating agent? There are many: phosphorus pentoxide, sulfuric acid, which can take care of the water. So, as simple as that. How it will proceed? The same phenomena, because it is having an alpha hydrogen atom, it will undergo some sort of tautomerism, the way I have shown in the previous case, and then this will be eliminated, the hydrogen and OH will be eliminated, and you end up with CH3 C triple bond N. So, CH3 C triple bond N, that is nitrile, is coming from the amide by dehydration and nitrile getting hydrolyzed to the amide by hydrolysis. So, this is another trick to make the carbon nitrogen triple bond and use it for the preparation of important compounds like amides, polyamides and all other important feature. I will tell another interesting features of nitrogen containing organic compound that I did not mention much. That is, if I write a benzene ring, now it is very clear, and remove one of the carbon by the nitrogen atom, then there are 5 hydrogen atoms now directly attached to the carbon, and one of the CH being replaced by the nitrogen. So, this type of compounds are carbon nitrogen compound, but I should say most precisely this is the heterocyclic aromatic compound. Heterocyclic aromatic compound. Why heterocyclic? Because heteroatom is present. Why cyclic? Because if I start from the one end, I am ending up at the same atom, and it is aromatic because it is just like benzene rings, but one of the carbon being replaced by nitrogen. So, it follows the Huckel's rule, that is planar conjugated cyclic compound having 4 n plus 2 pi electrons. So, all those rules being followed. So, this is an heterocyclic aromatic compound. Likewise, if I write another structure where it is the 5 membered ring, where one of the member is the nitrogen, and then the hydrogen atoms are there, each having 1. And if I look at this molecule, have I seen this type of molecule anywhere? Answer is yes, this is a heterocyclic compound having 1 nitrogen in the ring, and this compound is also aromatic in nature. So, we are able to get 2 types of aromatic heterocyclic compounds. What are those 2 types? One is a 5 member, another is a 6 member, and in each case, as we have focused our attention on carbon nitrogen compounds. So, one of the ring member is a nitrogen. So, one is called pyrrole, another is called pyridine, very common base. Very common base, how did I say? Because if I look at the number of electrons over there, I can see this nitrogen lone pair is very easily available, which it can donate to any acidic compound. So, this is a basic compound or pyridine is a very good solvent and also very good base, which is a heterocyclic compound having nitrogen in the benzene ring, one of the benzene rings carbon being replaced by N, and this is basic in nature because it fulfills the aromaticity very easily. But if I ask you what is the nature of this 5 membered nitrogen containing compound, is it aromatic? Yes, it is aromatic. How? Because I am taking the 2 nitrogen electron plus 4 from the conjugated system. And why it is conjugated? Because double single, though 2 singles are coming, but it is a delocalized thing. So, the Huckel's rule, if we recapture or recapitulate, it will be planar conjugated cyclic compound having 4 n plus 2 pi electron, where n is 1 in this case, that is 4 into 1 4 plus 2 6 pi electron, and exactly it is fitting that. It is planar, all are sp2 hybridized carbon, this is nitrogen, and 2 plus 2 plus 2, that is 6, 2 from 2 pairs of carbon and 2 from the nitrogen atom, and so 6 electrons rule is also being followed, and this is now fully aromatic in nature. But what is happening by this process? The nitrogen in this case 6 member 1 is available, the electron pair on nitrogen is available to other substrate. So, that is why I have written a term base, pyridine is a base, but in case of pyrrole I cannot write that term. Why not? Reason being, the lone pair of nitrogen is now being taken in the aromaticity gaining 5 member unit. So, it is not available. So, what happens? It acts as an acid. So, there is a very general question, nice question we asked, how come 5 member nitrogen containing delocalized compound, that is pyrrole, is acidic in nature, and pyridine, which is a 6 member nitrogen containing aromatic compound, is alkaline or basic in nature? Answer is, the electron density on the nitrogen of the pyridine is available to be donated, but that electron density of the pyrrole unit, which is a 5 membered, where its 2 electrons are being given to the benzene ring or the 5 membered ring to gain the aromaticity, is not available. So, it is electron deficient in that case. So, as per Lewis theory, an electron donor is a good base and electron acceptor is an acid. So, pyrrole is acidic in that way, pyridine is basic in that way if we consider. So, this is another interesting phenomena where we see the carbon nitrogen compounds are not only on the side chain or directly attached to the alkyl group, directly attached to the aromatic group, but it may be a part of the benzene ring or 5 member ring or 7 member ring or in higher series also. So, nitrogen's role is tremendous in biological system. I did not say anything about another important class of the carbon nitrogen compound. People say that antibiotics are, as I told you, that beta lactam related compounds, not one class, there are many classes of antibiotics. Beta lactam unit is very important, which is nothing but carbon nitrogen containing compound. Second portion came is the amino acid, which is the building block for protein, peptide, polypeptide. Third thing is, if we take the pyrrole units together, 4 pyrrole units being connected by carbon atom. If I write it in that way, it will be N N just I have written arbitrarily one structure where 4 pyrrole units are there. In between normally there are 1 carbon or substituted 1, just to fill the importance of this class of compounds, where 4 pyrrole units are on 4 sides and each pyrrole unit in the 2 position, and this will be 3, 4, 5 position, 2 position and 5 position being connected by another carbon atom, or it may be directly connected to another pyrrole unit. So, that sort of structural features makes a cavity, and this cavity is very interesting to fit many metal ions, and those metal ions giving that type of compounds very interesting feature, very interesting biological activities, very interesting color. And if I ask you, have you seen this type of 4 pyrrole units being connected through each one carbon atom or substituted carbon atom and making a ring, macrocyclic ring of that way? One interesting thing is that type of compounds in general are called porphyrin, or I should say polypyrroles, 4 units together. And this type of porphyrin in natural products we see is very much present in 2-3 interesting compounds what we know for everyday life. What is that? Why blood is red in color? Everybody knows blood contains hemoglobin. Heme is that polypyrrole unit where a metal ion is being there. So, heme, this iron is the metal ion. Like why the green leaves are there, why the leaves are green in color? Answer is very simple, that is the chlorophyll, and in chlorophyll the basic unit, structural units is the porphyrin, and this porphyrin means that 4 pyrrole unit being connected in 2 and 5 position through 1 carbon atom each. So, that makes a cavity, and in cavity the calcium or magnesium or many ions could be fitted, and different types of colored biologically active pigments and medicines are being produced. One simple example is heme, globin is the protein part. Second example is the chlorophyll, that is green in color, and third example is cyanocobalamin, little bit complicated structure, but basic unit is polypyrrole, that is present in vitamin B12. So, vitamin B12 is also a B complex, very important member. So, these are the important features of the carbon nitrogen compound in everyday life or in medicinal things or in other way. I should say one more thing to end up today's talk, that other than antibiotics, other than amino acids, protein peptides, other than the amides or heterocyclic compounds like pyrrole, quinoline, pyridine, pyrimidine, those are the building blocks of the life, DNA, RNA. Another important nitrogen containing organic compounds are alkaloids. So, alkaloids are by definition is alkali like compound, alkaline mostly in nature, obtained from natural sources, having nitrogen will have to have carbon and having some medicinal value. So, medicinally important nitrogen containing compounds are the alkaloids, which are alkaline in nature. So, that thing I did not mention. If I ask you, can you name some alkaloids? Yes, quinine, nicotine, pyrimidine, there are many alkaloids, and some of the narcotics also having the carbon nitrogen unit being present. So, to sum up, we have discussed about the importance of carbon nitrogen compounds and how to prepare them, especially for aromatic system. through the help of the nitro group and then by reduction. And to convert the nitro to amine is very simple reduction, and amine to diazo not much difficult, that is sodium nitrite, hydrochloric acid, diazotization, and then by using Sandmeyer reaction almost any functionality could be introduced, where the diazo group will go and the new group will come, and the use of those compounds in the functional group transformation. I will continue with other aspects of the carbon nitrogen compounds next time. Thank you.